Ladies and gentlemen, my name is Vesa Vuorinen. I am from Aalto University, Finland, from the research group of electronics integration and reliability. It is my pleasure to introduce you our studies on copper-tin indium system for low temperature wafer-level solid-liquid interdiffusion bonding. This work is carried out in Applause project in work package 4 in the task 4.3 bonding technologies for sensitive optical components. The development work has been done in cooperation with EV Group. First, a motivation. The novel concept of all silicon package has recently been introduced in the Handbook of Silicon-Based MEMS Materials and Technologies. It is our opinion that the low temperature wafer level metal bonding can be a key enabling technique for three-dimensional more than more integration. In 3D integration, the main challenges are related to how one can reliably bond materials with dissimilar thermomechanical properties. Here, our aim is to concentrate on different types of micropumps or micro interconnections, as well as the hermetic encapsulation of MEMS components. Why we decided to study the copper-tin indium ternary system? It is well known from development of low temperature lead-free solders that indium has stabilizing effect on the liquid phase. Based on the available thermodynamic description from the ternary system, it is possible to evaluate the effects of indium additions to copper-tin system on the interconnection microstructures as well as processing capabilities. Based on the thermodynamic simulations, we can conclude that we don't expect significant differences in the interconnection microstructures in comparison to the more commonly utilized binary copper-tin system. In addition, we see that the stabilizing effect of indium to the liquid phase increases the process window in the ternary system, indicated with the blue color here, in comparison to the more commonly used binary copper-tin system. Moreover, we can also see that when the liquid phase is completely consumed by the chemical reactions during the bonding, the remelting temperature of the interconnection should increase up to 600 degrees centigrade. Therefore, we expect that the bonding should be possible at the temperatures around 200 degrees centigrade, but still we should achieve interconnections which are thermally stable up to 600 degrees centigrade. Here the basic processing parameters are shown. During the bonding, wafers are aligned and preheated up to 75 degrees centigrade. At that temperature, the pressure is applied and then the wafer pair is heated up to the actual bonding temperature, which in our case were either 200 degrees centigrade or 250 degrees centigrade. The bonding time was 60 minutes, and after that the pressure was released and the wafer pair cooled down. In this test batch we had two different types of structures. The symmetric structure where copper, indium and tin were deposited on both wafers, and asymmetric structure where tin and indium was plated only on the cap wafer side. The bonding trials were mainly successful, so we were able to achieve high quality bonds down to 25 micrometer bump sizes and temperatures down to 200 degrees centigrade. However, there still remain some challenges related to the smallest micro interconnections, 10 micrometer interconnections and alignment marks. These challenges were our photolithography and etching processes. This slide concludes our findings on the interconnection microstructures. In the left hand side, we see the as-bonded microstructures, and we can conclude that at 250 degrees bonding temperature, the interconnections were mainly composed of copper-3 tin phase, and on the other hand, when bonding temperature was 200 degrees centigrade, then the microstructure was completely copper-6 tin 5 phase. The interesting phenomena was found out when we did some solid-state annealing, and we observed that these microstructures seem to be extremely stable against thermal treatments. Here we see the microstructures after 500 hours exposure at 150 degrees centigrade, and we cannot observe any microstructural changes. In fact, these similar results we have obtained also after 1000 hours. So to conclude, low temperature wafer level copper-tin indium SLID bonds were successfully fabricated, bonding temperatures down to 200 degrees centigrade. In mechanical tensile testing, we didn't observe any failures which would propagate through the actual interconnections. All failures were adhesion failures at either silicon titungsten or titungsten copper interface, and the fracture strength were higher than 25 megapascals. We still had some test wafer manufacturing related challenges in our lithography and etching processes that caused that the bonding of the smallest 10 micrometer features could not be verified. In addition, the asymmetrical 200 degrees centigrade bonds failed. The addition of indium to the traditional copper-tin system seems to significantly stabilize the microstructure, especially copper-16 indium 5 phase. Since these preliminary results are very promising, the further studies will be towards even smaller microcontacts and thermomechanically more challenging applications like bonding silicon MEMS or MEMS components to glass, sapphire or germanium caps. In addition, functional and mechanical reliability performance needs to be verified. If you are interested, please check our conference paper which was presented in ESTC 2020. It is now available in IEEE Explorer. Thank you, and if you have any questions, feel free to contact me via email.